Okay, let's actually do a power series example, sort of explore it thoroughly. This example right here that I've written, first off, notice it's centered at 0, right? Since it has x to the n in it. It's not x minus 5 quantity to the n or something like that. And we want to find the radius and interval of convergence. Those are the notions I introduced in the terminology video. And that we want to actually figure out exactly where this converges. My letters are a little off here. Okay, VER. All right. So, to get your hands on this, you got to start just writing out. I mean, I think one nice thing to do is just write out some terms of the series. Like, if we plug in n equals 1, we get x over 1 times 2, right? So we get 1/2 x. If we plug in x equals 2, we get an x squared on top, and we get a 2 and a 2 squared on the bottom. That's 1/8 x squared. You can keep going. I think the next one is 1 over 24 x cubed. And can I do it? 1 over 64 x to the 4th. And, I mean, maybe it's not that important, but it's nice to get a little bit of feel for what this looks like. I guess what I say it's centered at x equals 0 because it's sort of, again, this word obvious, it sort of obviously converges. If we plug in 0, all the terms of the series become 0. And so, right, so when this just equals 0, when x equals 0. So that's definitely converges because it's a finite value. So that's the center. And then we talked about finding, or we mentioned there's this idea of the radius of convergence. But what if we wanted to know if it converges at some value? Like say, again, I just want to explore a little bit before I sort of do the formal approach that everyone uses. But let's just ask, does this converge when x equals 1, say? Well, what if we plugged in x equals 1? If we plug in x equals 1, we just get, I can plug x equals 1 up in the written out by term, but in the summation notation, it's just 1 over n times 2 to the n. And it may not be obvious, but I will say you could even just immediately do a comparison. There's different ways to approach this. We could use the ratio test, because that's actually, we saw a very similar example. I think the n was on top. We had n over 2 to the n. We did the ratio test on that. But you can notice that this is less than, yeah, since the bottom it's bigger, this is actually less than, I claim, I don't know why I said less than or equal, it's actually strictly less than just the sum of 1 over 2 to the n, because as n grows, right, for n greater than 1, for n greater than 1, n times 2 to the n is greater than 2 to the n. So the bottom is bigger, so when it's flipped over, it becomes, the fraction is smaller, and then the sum is smaller. And this is a geometric series with r equals 1/2. And so that's geometric. Geometric. R equals 1/2 converges. So yes, this does converge. Yes, the series does converge. When x equals 1. And you could keep doing that. You could keep exploring different values. You could plug in different values, try to come up with arguments each time. Just think, if you plug in a specific x, you get a specific infinite series, and we've now spent this time developing some tests to figure out when specific infinite series converge. But what if we wanted to do something a little more systematic? So it turns out that the ratio test is really helpful here. And let me just mention, so the term of the series is called a sub n, right? We actually wrote c sub n x to the n, so c sub n would just be the part that's doesn't have the x to the n, right? Oh my god, those both look like a's. That's supposed to be a c. So that's a c sub n equals that. But a sub n is the whole thing. And so if we want to approach this more systematically, it turns out the ratio test is quite nice for power series. Because there's this x to the n, you'll see how this works, actually. Let me just do it. So to be more systematic, use the ratio test. Turns out to be a very helpful thing for pretty much all power series. And so here, like I said, a sub n is x to the n over n times 2 to the n. Remember, to do the ratio test, we also need to write down a sub n plus 1, replace n with n plus 1 everywhere. So we have an x to the n plus 1 in the numerator, and we have an n plus 1 times 2 to the n plus 1 in the denominator. And then the ratio test says to compute the ratio of consecutive terms. So to compute the limit as n goes to infinity of a sub n plus 1 over a sub n absolute value. This actually predicts absolute convergence, which is nice. And so if we start to plug these things in, so the top, right, this is on the top. The a sub n plus 1 is on the top. The a sub n is on the bottom. But it's a fraction, and a fraction on the bottom we can just think of being multiplied and flipped over, right? We flip it over, we can think of multiplying it instead. So let me just write some of this out. So the limit as n goes to infinity, I can basically think of writing the n plus first term right here. And then instead of dividing by the nth term, I can multiply by the reciprocal of the nth term. And so that's like that, right? And all of a sudden, and already you sort of see there's some nice cancellation, maybe. You know, x to the n plus 1 over x to the n is really just x, because there's one more x on the top than the bottom. There's one more 2 on the bottom than the top. And so that simplifies to the limit as n goes to infinity, absolute value. We have an x on top, we have an n on top. We have an n plus 1 times 2 on the bottom. Now, the absolute value sign is to make everything positive, right? But n plus 1, and 2 are all positive. So we could actually rewrite this. We can sort of bring the absolute value signs in. The only one thing that we don't know is positive is x. So we can write as that. And actually, the absolute value of x and the 2 don't depend on n. So we can actually pull those out of the limit. Right, I can pull those out, and we have just a limit as n goes to infinity of n over n plus 1. And there's various ways to attack this limit. You've seen it enough times now. I think you probably know that, you know, the plus 1 becomes negligible as n gets large, and this is going to go to 1. If you wanted to be a little systematic, you could think about multiplying the top and bottom by 1 over n and going through that way. But either way, this equals 1. I'm not going to do the details of that. Let you do that yourself if he doesn't seem familiar. So, okay, so the ratio test spits out just the absolute value of x over 2. I'll just write that down because I want to say that. So the ratio test spits out absolute value of x over 2. But what does the ratio test say? The ratio test says that if that we compute that limit, and if that limit's less than 1, then the series converges, and if it's greater than 1, then the series diverges, and if it equals 1, then there's no information, right? So let me just remind you, this is, if we call this L, this limit here, then the ratio test says that the series converges. Series, there's 3 possibilities, right? It converges if L is less than 1. It diverges if L is greater than 1. And actually, it tells us nothing if it spits out, if the ratio test spits out L equals 1. But here our L is this absolute value of x over 2. That is our L. That's what the ratio test spit out. And so the series that we started with converges. So our series converges if x over 2, absolute value of x over 2 is less than 1, which really means that the absolute value of x is less than 2, right? We can double both sides of that. It diverges if the absolute value of x over 2 is greater than 1. It's the same thing as absolute value of x is greater than 2. And and we get no info. We don't know if the ratio test is not predictive, if this equals 1. I'll write that better. So that means if the absolute value of x equals 2, or really if x is plus or minus 2. Okay, so we can start to draw, just like we did in the sort of the general video. We get this, if we draw a number line, like this, values of x, 0, 2, minus 2. We know it converges we know it converges from here to here, right? But what about so that's actually something, that's before I move on and say, but I should say, okay, that actually tells us our radius, right? Because it converged, quote, obviously at 0, and it converges all the way out to 2 and negative 2. So the radius r is 2. Good. What we don't know is what's going on here and here at 2 and negative 2. So these are still question marks. Okay. So we haven't quite pinned on the full interval yet. We need to analyze these 2 points separately. But we do have the radius. The radius is 2. So now if we want to talk about the interval of convergence, we need to ask what happens when x equals plus or minus 2. Plus 2, minus 2. There's separate questions. It might be different, and we will see here they are different. So if we plug in 2, for example, so that all you can do is plug in. The ratio test didn't tell us anything, so we've got to go back to the example, the series itself, and actually plug in the value. So plug in x equals 2. So we'll do that first. We go all the way back to the beginning. Here was our series. This is our series right here. So I'm just going to write the series again and then think about plugging in x equals 2. It's probably the best way to do that. So the sum from 1 to infinity, x to the n over n times 2 to the n. Well, if we plug in 2 for x, we get 2 to the n over n times 2 to the n, which, voila, cancellation. And we actually just get the sum of 1 over n. And that is a famous series, right? What's it called? Say it with me. You know what it's called? The harmonic series. This is the harmonic series which diverges. We know that this sum crawls off to infinity. So the power series does not converge at x equals 2. So it doesn't converge at x equals 2. What about minus 2? Well, maybe I won't write it again, but now if we plug it in for the original series, but we get minus 2 to the n over n times 2 to the n. And, you know, the minus 2 to the n might look a little weird to you at first. You could start plugging in values. And in fact, you would notice that you would get something, it would alternate plus or minus. And you basically have a 2 to the n on the top and a 2 to the n on the bottom, which would cancel. So in fact, if you're not sure about this, you should write out the first 2 terms and see that this is actually happening. But turns out one way I can think about this is I could actually break apart the minus 2 to the n as minus 1 to the n times 2 to the n over n times 2 to the n. That's also something that's allowed with as long as it's the same power, right? And now the 2 to the n's cancel again, and we get this sum, minus 1 to the n over n. And now this is an alternating harmonic series. It starts with minus 1, I guess, instead of plus 1. It starts with minus 1 plus a half minus a third, but still, it's the same thing up to a minus sign. So this is the alternating harmonic series, and something we've explored before. This is something we've explored before, and we know it converges. Okay. So very excited. So now actually, that means we actually know what happens at every single point on the number line. Right, if I go back up to my number line up here, we know this is the green area is the good area, right? That converges. Outside, maybe I should use red or something outside. Oh, I should make it thick again. We know if we go out here past 2 and minus 2, this is bad. Oh, hello. That's way too big. Change my pin width. This is bad. That's bad. But we also know what happens at 2 and negative 2. So in fact, let me just draw this one more time. Yeah. Let me make this a straight line. Okay. So here's my x-axis again. So we're to sum up. I draw my 0, my 2, my negative 2. Let me put little bubbles around 2 and negative 2. Let's put our green again here. And we know it converges here. Good, good, good. Oh my God, I use that big check. And then we know it diverges outside of 2 and outside, basically more than 2 units away from the origin. And we actually know that it converges when x is negative 2. So in fact, I'm going to bubble this in, and it diverges when x is 2. So maybe like that. Or, a way people would probably draw this is just something like, I could also draw it more like this, like a bubble and then a line and then an open circle. So you could draw like that if you want to. But basically that's the interval of convergence. So, and we can sum up the interval of convergence. I wanted to write it in math, not with a picture. Convergence is minus 2 less than or equal to x strictly less than 2. And the radius is 2. Okay. So we completely understand this power series. We know every value of x for which it converges and every value of x for which it diverges. We can classify every value of x. Okay, great. I'll stop there.